Welcome. My name is Noel Gorlick. I'm one of the co-founders of Earth Engine. Today we're going to do what we call Earth Engine 102. This is our intermediate classifiers class. What I'm hoping that you learn today is that it is super easy to do multi-temporal stuff using Earth Engine and sensor fusion. So those crazy words that mean really hard stuff when you're doing it yourself actually work out to be about 4 or 5 lines of code when you use Earth Engine to do it. On purpose. Like we made it we intentionally tried to make that possible. I actually did this workshop on Monday, and it was 3 hours to the end, and then really the punchline was, and here are the right 4 lines of code you need. You just needed to learn what those 4 lines of code mean. So that's what this will be about. I have a tiny number of slides. Really, I just have a little cartoon to sort of get us on the right page. And then I actually don't have scripts. If you were here yesterday and you were following along with the scripts, we're going to do all this live. And in fact, we'll probably alter what we do based on a little bit of feedback from you guys as we decide along the way how we're going to do this. But this one in particular, let me rephrase that. Earth Engine does some really amazing, crazy, large-scale things, except this part. If you've got 100 million training points, Earth Engine is not the place to use those because our classifier system just can't handle that right now. So this is a fun class. You're going to learn how to do a really amazing type of classification. But I'm going to point out all the spots along the way where Earth Engine can't do stuff. There are certain types of limitations on the system. I'm going to point them out. And in fact, I'm going to point them out by way of you hitting an error. And then I'll say, OK, here's how you work around that error. It's dumb. I hate it. But this is what we have to do for now. OK? So I hope you'll be excited. I hope you'll enjoy it. But also, it's going to be a little bit frustrating, because you're just going to keep hitting error after error, and we're going to work around them. OK, so what we're going to end up doing is supervised classification. And I got a little cartoon here just to get us all on the same page. Typically, you are going to classify an image or a table or something like that. And to do that, you need to provide some supervision to the classifier. And that often comes in the form of a land cover map or a crop map or something where you know what's there on the ground. And so we'll assume for a minute we've got a land cover map with some urban points or some areas that we know are urban, some areas that we know are forest, a road, and some water. And so you might pick 4 points from that map, or you might manually say these 4 points are these types of land cover. And then there's going to be a set of covariates that you're going to want to use for training and prediction. So for every one of those points, you're actually going to extract all the values from the covariate stack, and that becomes a table, which is what we use to train the classifier with. So every single point ends up with a value for every single band, including the class band. And each of these rows becomes what's called a feature vector. And this is just super basic supervised classification. You probably all know this. But in Earth Engine, this feature vector can be pretty much anything you want. So you can be classifying on Landsat data, and maybe you want to throw some elevation data in there, or some precipitation, or socioeconomic status. Anything you can get into a raster, you can get into this feature vector and put into the classification system as part of your covariates. You just have to have values for all of your training points. You're not allowed to have missing values in any of these pieces for the classification system. So when you do all this, you end up with a table. That table's got 1 row per point. Maybe you had a polygon and you were extracting all the points in that polygon. You'll still get 1 row per pixel, basically. And then there's columns with your covariates. And in this case, I've got time, NDVI, and elevation, and I'm predicting a class, 0s or 1s. So that's what the data will actually look like when we've got it in hand. We stick that into a classifier to train it, and then we throw that at our original image or other images that have the same shape as our training vector, and we can do prediction and classification with it. Here's where the constraints start out. This table in Earth Engine, certain types of tables are limited to 82 megabytes in size. So all your training data, unfortunately, has to fit into an 82 megabyte table right now. I hope to fix this in January, but no promises. That roughly means about 1 million features. You can't really tell how big a feature is. You can guess. You've got maybe 10 double values. That's about 80 bytes. There's some overhead, so we'll round up to maybe 100 bytes. So if you're using 10 bands and you end up with a 100-byte feature, that means that you can have less than 1 million of them, right? About 800,000 of those in your training data. So what that means is you just need to be a little judicious in picking your training data. You can't just take the entire world and stick it in a classifier and hope for the best. I want to make that happen. You just can't do it right now. As I already said, the data can't be sparse. No holes in your training data. That's not allowed. And the classes that we use need to be small numbered integers. So we can't classify on strings. You can't say this is forest and that's water. You can say forest is 0 and water is 1, and that works. But the class number is used in quite a number of places inside the classifiers and outside the classifier to mean to set limits. So for instance, if you're getting a confusion matrix from your classified results, that confusion matrix has rows and columns for all of the classes involved. So if your classes run from 0 to 10, you're going to have 11 columns and 11 rows in your confusion matrix. If your classes run from 0 to 1 million, you're going to have 1 million rows and 1 million columns in your confusion matrix, and no one's going to be happy about that. And even worse, if your classes are 0 and 1 million, you're still going to have 1 million rows and 1 million columns, and 999,998 of them will be empty. So you really want those numbers to be low numbered integers, because lots of pieces just assume that they're going to work their way through all of the classes, and it doesn't know what the possible classes are, so it just starts at 0 and works up to the maximum class. This is especially true in the case of the SVM classifier. It does some kind of combinatoric mixing of all of the classes, and it doesn't know which ones there are, so it does combinatorics between 0 and 1 million, and it blows up somewhere around 20, or maybe 50. So, small numbered classes. Okay? All right, that's all the slides, that's all the boring stuff. Everything from here on in is hands-on. This slide deck has a lot more stuff in it about the classification system. If you want to go through it or have it, there's a link to it, and you can use it as a review and just a general primer on the classification system afterwards. But right now, what we're going to do is go classify some data. So if you are brand new, the Wi-Fi is Google Guest. There's no password. You better have an Earth Engine account if you're in this class. That was a requirement. And we're going to get to the code editor. And now we're going to ask a question. Who works with Landsat? Who works with Sentinel? OK? Would you rather try this on Landsat data, because most of you are familiar with it? Or would you rather try this on Sentinel data, because most of you are not familiar with it? So who wants to vote for Landsat? Oh, poor Landsat. OK. Who wants to vote for Sentinel? All right. We're going to do some Sentinel classification. Now, the hard question, or it's easy for me, but you guys got to answer. Sentinel 1 or Sentinel 2? 2. 1. Oh, sorry. 2. Everybody for 2. Everybody for 1. OK, so 2 wins. That's what we'll start with. But I'll tell you a secret. At the end, we're doing sensor fusion, so we're going to bring in Sentinel 1 as well. So you voted exactly the way I hoped you'd vote. So everything I have prepared will work. Yeah, 40-second workshop for the year. I have a pretty good dial on you guys. OK, so if you don't use Sentinel 2, it looks a lot like Landsat. It's an optical imager. It doesn't have a thermal band. It's got about 13 other bands, including 4 near-infrared bands, which are pretty good for crop classification, and some cloud bands that make it that are supposed to make it easy to mask clouds in. It doesn't always work, but at least they have the cloud mask, and it kind of works. So yesterday we made composites trying to get rid of the clouds and not, just we worked around the clouds yesterday. today, we're actually going to do real cloud masking using the provider's cloud mask. So in this case, the Sentinel-2 cloud mask to do this. If you haven't already thought of it, many of you are about to ask the question, do you have Sentinel-2 surface reflectance? And the answer is, I do not. There hasn't really been a consensus on what kind of surface reflectance to do for Sentinel-2. Everybody that has used Centicore has been quite unhappy with it. So we haven't made a decision about what to do yet. Since then, like this week, the Sentinel-2 folks have started releasing L2A surface. They've started releasing surface reflectance data. So we may just go and bring that in. But I think really we can still do better. So don't hold your breath, but we know it's important, and we're trying to work out how to get you Sentinel-2 surface reflectance as soon as we can. So all that said, doing the cloud masking is not too hard, but there are some fiddly bits specifically around the bits, right? The cloud mask is bit packed into a band. Pulling that out is a little fiddly. Most of you are brand new, so rather than trying to walk you through how to do that from scratch, I'm going to go get an example, and we're just going to start from that example. So here in our code editor, down at the bottom, there is a whole section called cloud masking. Cloud masking, there it is. And we are going to go get the Sentinel-2 cloud masking example. And I'll walk you through what's in this, but I didn't want you to have to type all this stuff. And we're just going to cheat and start with this. Everybody got that? Any issues? This is our first connectivity, so make sure everybody's up and running. All right. If you're new, it's definitely a hands up kind of thing. If you have any problems, if we're going too fast, just raise your hand and let us know. And these wonderful gentlemen will come by and solve your problems, or at least your computer problems. So just like yesterday, we're going to narrow down to something small so that we're not trying to wait for data. We're just going to look at the Washington area right now. Go ahead and run this so you can see what it does, and then we'll walk through what's actually in it. That is a nice, pretty Sentinel-2 cloud-free mosaic, give or take. If there's clouds in there, they're really hard to see. So we're going to call it cloud-free and cloud-free enough. Okay? Let's see what's in it. It's pretty simple. We've got a function that actually goes and gets the quality band. It does the cloud extraction and masks the image with it. And we'll go into detail in that in just a second. But then we are getting the Sentinel-2 collection, filtering it to 1 year's worth of data, filtering out the obviously cloudy images. So the images come with some metadata that say how cloudy the provider thinks it is. And if it's an image that's more than 20% cloudy, let's just not even bother with it for right now. We're just going to worry about the mostly cloud-free images to begin with. And then we're going to apply our cloud masking function to all of the images in the collection, so they are then hopefully cloud-free. They'll have holes in them, but they're cloud-free. And then from what's left, we're just going to take a median composite. Again, for the whole year, this may not be the best choice, but it's an image to start with, and we will do better as we go on. And then we just stick it on a map.
Question.
Yes?
So the cloud score is just for the whole image. It's not in terms of mesh.
It is for the whole image. It's just one number that comes with the metadata for the image. Yep, so the filtering here, the cloudy pixel percentage is how many of the pixels for the whole image are cloudy, or tile. How many pixels for the tile are cloudy? So I can't. So our function that does the cloud masking, like I said, is a little bit of fiddly. Inside of each image, there's a band called QA60. That means the quality band for the 60-meter resolution bands. Sentinel-2 comes with 10-meter bands, 20-meter bands, and 60-meter bands. And the 60-meter bands are basically the cloud bands. And so the cloud masking happens from the 60-meter bands. It turns out that the 20-meter and 10-meter QA bands just have never been populated yet. So there is better quality to be had yet, but the provider just doesn't do it yet. So for each image, we're going to get the quality band. The clouds are identified in bits 10 and bits 11. So for each pixel, there's a composite number, and bit 10, if it's on, means cloudy, and bit 11, if it's on, means cirrus, a cirrus cloud. So if either of those bits is set, we don't want this pixel. So we make a bit mask that is a 1 in bit 10, and another one that is a 1 in bit 11, and we apply that bit mask to the QA band. And that's what's going on here. The QA band ANDed with our cloud mask. If that's a 0, it's a good pixel, or at least it's not a cloudy pixel. And the same thing just below it, the QA band ANDed with the cirrus bit mask. If that's a 0, it's not a cirrus pixel. So we do the bitwise ANDing of our two masks, and then AND together those two results. If it's not a cloud and it's not a cirrus, good pixel. We get a 1. If either of them is a 1, it's not a pixel we want. And if both of them is a 1, it's not a pixel we want. So we're making a mask on a per pixel basis about whether this is cloudy or not. And then we saw this yesterday. We just update the images mask with that new mask. These images are scaled by 10,000, so we're just going to scale them right there on the line. And then we're getting rid of the quality band because we've already used it. We don't want to go into our classification. We don't want to deal with it anymore. So we're selecting all the bands that begin with B and no others. So B dot star. Begin with B, followed by any letter and any number of any letters. This is a regular expression that means anything beginning with B. The QA band is Q. There's 3 QA bands. We get rid of them. And this will just leave the reflectance bands. And then, because we're going to be modifying, we're going to be filtering these images down and doing stuff with them later, we're going to make sure every image has a time so we can do time filtering on them at a later date. And then we just return what's left. Does that all make sense? Kind of similar to what we did yesterday, a little more detailed. You got a nod. Yes or no, one of the two. OK. So as you saw, that will make a nice, pretty median composite. It does a nice job, right? The Sentinel-2 data is pretty. It's good data. So we have an image that's one piece, or we have covariates, right? We've got all these reflectance bands. That's one piece of the puzzle that we need to be able to do classification. The other piece that we needed was some kind of supervision. So for right now, I'm going to teach you a few bits of the code editor that we didn't really use yesterday to allow you to create a little bit of supervision just so we can get a classification started. And then we'll do better, or we'll do something else in just a minute. So pick your favorite location. I recommend Washington so that you can see what we're doing all together. And what we're going to do here is try to identify crop and agriculture, urban, and water, just because they're real easy to see here. And the way we're going to do that is manually. So over here in the drawing tools, there's different kinds of things you can draw. Go ahead and click one on the polygon, and it will make a new geometry. At the very top of your script, it has this thing called geometry. It's got a geometry layer here. And we're going to do some fiddling with this first. I don't actually want a geometry. What I want is a feature collection, right? I'm trying to do rows in a table. That's a feature collection. So I want to turn this geometry, or this thing I'm about to create, into feature collections instead. So if we hover on the imports and go to this layers gear icon, we can change what it is. So click on the gear icon. And now some configuration. We're going to call this first class urban. We're going to make this thing we're creating a feature collection. And we're going to give every feature in this collection a property called class. And it will be class 0. The urban stuff will be class 0. So 4 things there. Click on the gear, change the name, go to a feature collection, add a property called class 0, or class of 0. If you had trouble with that, don't worry about it. We're about to do it 2 more times. If you got it to work, click on New Layer and do it again. Gear. This one we'll call Veg. Feature Collection Class 1. Whatever you used for the property name the first time here, you need to use again.
If you have trouble, just raise your hand.
Yeah. Okay. So the first one, we gave a property called class, and it had a value of 0. The second one, these second set of points, need the same property name. They need to match. And these will be class 1. And we'll do it one more time for water. And if you want to change the colors, you can, but I did this in this order because those colors work out pretty good for what we did. You need to see it? You don't need to see it. I don't need a fourth class, but okay. Click on the gear. If you haven't added a layer, add a layer. Click on the gear, change the name, change the type, add a property, class 0, 1, or 2. If it worked, at the top of your script, you should now see 3 variables that are feature collections. If those don't say feature collection, you missed a step. If there aren't 3 of them, you missed a step. If they don't have those names, that's okay. Problems? Anybody? Sweet. Okay. Now we need to go collect a little bit of training data. Oh, problem? There's click on the hand, click on the item, and there's a delete button. But I'll show you that in just a second. Okay, so for each one of these, we now want to identify some points that are of this class. And you have the options of dropping individual points if you want to be precise. You can drop a line, and we'll take all the pixels that are under that line. Or you can drop a polygon, and we'll take all the pixels inside that polygon. But as you might remember, we only get about 100,000, about 1 million points, and probably a little less because these are double points and et cetera. So you need to be a little judicious in what you pick for your training data. I'm going to pick a line, and I'm going to start up here in the shallow bits of this water and kind of meander around a bit to try to get multiple colors of water in there. I could draw a big polygon over the entire river, but I don't think I need that many points. More points of the same type are less valuable. You want more points of different types. So shallow water, deep water, turbid water, whatever. So a line for the water. For the urban area, we click on the urban layer, and I'm going to drop a polygon here on downtown Baltimore. If you don't like it, you can click on the hand, click on the polygon, and then just punch delete. Or you can just change it now. Once it's highlighted with the hand, you can drag around the points and just change it. And out here, all this stuff is pretty clearly veg. The goal here is not a highly accurate classification. The goal here is just get some training data. And then click in several spots. Yeah. Don't drag, just click. There you go.
Oh, it's here? Okay.
Yeah,
Good,
it's
good.
hard
Yeah,
to see.
it's here.
Are you using Internet Explorer? No. So don't drag, just click. There you go. The drawing action is not a drag, it's just a click. You're dropping a point. that's one of the points in the polygon. So click, 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 click. Okay, everybody have at least 3 points, or at least 1 point in each class? Yeah, I guess I'm asking the wrong question, aren't I? I didn't introduce these guys. This is Michael. Michael's a back-end engineer. He built a whole bunch of the features that you, oh, actually he's a front-end engineer too now. He's a general-purpose engineer. Full-stack engineer. He's been lately responsible for the publish an app feature. So if you like that, he would very much like to know about it. And the other guy, Nick, he's one of our developer relations guys who helps me do trainings. He does trainings himself. We do science outreach. And this is probably his 20th training for the year as well. Okay, we have training points. Let's do something with them. So now we have 2 of the 3 pieces that we need for to making our table. The next piece we need is our table. So we're going to go get some training data. We're going to go extract this training data. So training. So we're going to take our composite, and we're going to sample it at all these points. And the easiest way to do that is with sample regions. And if you weren't here yesterday, I just did an autocomplete to fill in a bunch of argument names. I care about that, that, and that. And we'll deal with the rest in a minute. I have these 3 feature collections that I'm using for my training data. I need to combine them together. So the collection I want here is actually urban merged with veg, merge with veg, merge with water. So just stick them all together. And the properties that I care about are the class property that I've typed in. And I want to do this at 20 meters, and I want it to give me geometries. I'll explain that in just a second. And then I'd like to know how many points I've got when it's done. So I'm going to just print the size of my training result. You are extracting the spectral signatures right now. That's what sample regions is doing. At each point, extract the spectrum.
How about if I have from the field?
From
the field, let's say.
So if you have a bunch of N members that you already have in a library, you can train with those just fine. You would be training with a table. We're making a table. You would already have a table, right? So each N member spectrum would be run 1 row in the table with columns for the spectral properties. You'll see in just a second as we look at one of these. So you could print the whole training table, but it's 182,000 lines and your browser would crash. So all I care about is knowing how many I've got and kind of when it's finished. The sample regions call is an aggregation. It happens once. It doesn't happen every time you zoom and pan. Aggregations happen separately. So I just want to know when that aggregation is finished. And if I print the size of the training table, it only knows that once it's done. And coincidentally, I'll know how many training points I have. We might also want to look at one of them and see what it looks like. And so it's got top of atmosphere reflectance in all of our bands and a class band or a class property. And of my 189,000 features, I don't really know how many went into veg and how many went into water. And that's the thing I like to know. You may not care, but I like to know that. So I'm going to run a reduction on the training data. And I'm going to get a frequency histogram of each of the classes, so I just know how many there are. Oops, sorry about that. There we go. And as we add these things and we keep click and run, you'll note that they pop in really fast the second time. That's because they've been cached, and we don't have to recompute that. But this histogram hasn't been cached yet. It's got to go through the whole table. And there we go. So what this tells me is I have way too much veg, but it doesn't really affect what we're doing too much. If I had no pixels or a couple pixels, then I might be worried. But this distribution skew doesn't worry me too much for what we're trying to do right now. I see lots of squinting. Anybody having trouble? Yeah. Well, yeah, as soon as we're done with the toy, well, that's what we're doing. Okay, who doesn't have a training table? Do you need help? Not both of you. Sorry. Anybody else? Okay. Oh, you need some help?
Oh, it's just slow again.
So if you happen to have more than about 100,000 points, the rest of the steps are going to go kind of slow. So you might want to make your polygons smaller, or you can just wait. You know, it won't be too slow, but I hate waiting. All right, so if you have a training table, we're now ready to build a classifier. And this is pretty straightforward. In the Docs tab, you can see that we have a bunch of classifiers. Cart, continuous naive Bayes, decision tree, minimum distance, many, many classifiers. In reality, people only use about 3 of these. People use cart when they want a lot of control over what the tree looks like. They use random forest when they don't really know what they're looking for, and random forest will just kind of find it. And they use SVM because they read a paper that says SVMs are cool. There's a really nice paper on hypertuning for SVMs. If you can get an SVM hypertuned, they're really cool. But that is really, really hard. There are other libraries outside of Earth Engine that are all about finding that hypertuning. We don't have that yet. Most people that use SVMs in Earth Engine sort of cut themselves in the process of doing it. Because they're really finicky kind of classifiers. But people use them. Like there's lots and lots of people that have made SVM work. Today we're going to build a random forest with this data. And the way that works is an EE classifier random forest. You do have to spell it correctly though. Now, these classifiers are used inside of Google for all kinds of stuff. We just tapped into a Google library, and so most of them have pretty good defaults, except for random forest. Because there's just a wide variety of the number of trees you might want for random forest, it doesn't guess. If you give it no arguments, you get one tree, which is neither random nor a forest. So I recommend that you specify some number of trees. For my general rule of thumb for starting is about double the number of covariates I've got. So I've got about 10 covariates. I'm going to go with about 20 trees. We can play with this later. This number is not super important. Don't make it 1,000,000. Don't make it 1. Somewhere in between, perhaps on a logarithmic scale. And then we need to train it. The train function wants to know what your table is and which property is the supervision property. And we're done, sort of, depending on your goal. You can actually now just get a confusion matrix and a resubstitution accuracy straight out of this classifier. You do have to spell, though. The train call on the classifier doesn't actually do anything. It just sort of links a few things together and says, here's the data you're going to want. Until you actually use that classifier for something, it doesn't ever get built, because it might take a while, and we don't do anything we don't need. And so the first time you try to use the classifier, it will actually get trained and built. So a lot of people say, well, I extracted all my training data, and I built my classifier, and then when I tried to classify the image, it blew up. That's probably not actually what happened. It may even be that trying to extract the training data never finished, and you just never see that until the classifier gets built. So this is running. What it's doing right now is it's taking all the training data, it's building the trees for the random forest, and then it's classifying that data again with the trees. So we have a truth, right? We have a supervised class that we gave it, and then it's going to generate a supervised it's going to generate a predicted class, and it's doing a confusion matrix between those two. This is simple resubstitution accuracy, which is terrible. We're only doing this as an exercise. You really should never use resubstitution accuracy. This is going to be a ridiculously high accuracy number because I am really good at looking at an image and saying, that's all urban, and that's all water. And the likelihood of me mixing up urban and water myself is very low. In fact, I can often get this number to be 100%, 99.9% accuracy. I'm really good at picking homogeneous data. So resubstitution accuracy only tells you how homogeneous was your data. Don't try to use it for anything else. Don't really even use it. It's not a thing you want. To try to figure out if we did a good job or not, we should use some other kind of validation for our accuracy assessment. And one of the things we can do, the second thing we can do that's a step up from resubstitution, is to do holdout validation. So I've got 189,000 points. I can sacrifice 10 or 20% of those pretty readily to have a validation data set. So we will do that. Before the training step, I want to pull out 20% of the data. And here's how you do that. There's a bunch of ways you can do it. If you don't want to draw some more polygons, this is the way to do it. We're going to give each feature a random column, just a number between 0 and 1, evenly distributed. And then for the validation, we are going to take any of those rows that have a, come on, I can't type and talk at the same time. There we go. We're going to take any of the rows that have that random number less than 0.3. That should be really close to 30% of our data. And then everything else will stick back into the training variable. All right, so random column added a property called random because I didn't tell it to call it something else. We're now filtering the table on that random property. 30% for validation, 70% for training. LT less than, yes, less than. Uh-huh. It's between 0 and 1. Yep. Normal, a uniform distribution of numbers between 0 and 1. There's one sticking point here that will keep this from working. We sampled a bunch of data up here, and sample regions is smart enough to say, OK, you sampled these bands. That's probably what you're going to train with. And so it adds metadata to that table indicating what the bands are. But now we're fiddling with the table, and we're adding more columns. And if we try to run this right now, train will go, hey, I don't know what you're doing. There's extra columns in here. What do you really mean? So we need to tell it which columns we're actually going to be using in the classification. And we can do that right here by just specifying the band names of the composite. I sort of sidestepped you around the error that you would normally have hit here. I should have let you hit the error. Let me show you what it looks like first. There we go. Input properties must be specified because we fiddled with the properties. So you need to specify input properties. That's done that way. And instead of getting a confusion matrix with resubstitution error, we want an error matrix on our classified data. So validation, classify with our classifier, error matrix, class versus classification. So take our validation data, classify it with our classifier, generate a confusion matrix, but it's not really a confusion matrix because that's a special term. It's an error matrix comparing the class property, the one we gave it, versus the classification property that's being generated by the classifier. So those are the names of two properties. And then we just get an accuracy out the other end. The confusion matrices and error matrices have consumer's accuracy and producer's accuracy and kappa, and you can actually get the whole matrix if you want, but I stopped caring with the accuracy number. Anybody get a new accuracy yet? Nope, okay. This is about the time where we start overloading the Earth Engine servers because we're all doing the exact same thing at the exact same time. Fortunately, all of my on-call guys are here, so you're not actually waking anybody up. You're getting 0. So you mistyped one of these two words. Yep. Yes! 42 trainings for the win. Oh, hey, you're right. I made a mistake. This is the lower 30% of the data, and this is the upper 30% of the data. I threw away 40% of my data. Very good. Thank you. This should really be 0.3. But I had a lot of data, so I don't expect that to make a big difference in my classifier, so I'm not going to rerun it just yet. I do want it to go faster, however. We'll give it a minute. If it doesn't work, if it doesn't finish real soon, we'll make it smaller. The thing that's going really, really slow right now is actually this. Classifying a table just happens to go slow in our system. Again, when I get to go back to Zurich and type some code in for the first time of the year, I hope to fix a lot of this stuff and iron out a bunch of the problems we've discovered over the year. And that's one of them. All right. I'm actually going to bump this down to 5% just so this runs faster. No problem? Question?
Just a question. So this accuracy is telling us we have like a portion of our training data reserved, and we are comparing that with the classified image. Would that be an equivalent of having a field ground with data, and like going and collecting that?
No, that'd be better. This is a very long time to wait for a really bad punchline, which is this isn't a great way to do it either. Field data is way better if you've got it. But you're probably actually going to use the field data for both training and classification and validation. So you're going to do the same thing. If you go collect 100,000 training points out in the field, you're going to do the exact same thing here. But then it's a perfectly valid way to do it. I'll explain. I learned something in the past month. I'm trying to get to the point where I can show you the thing I learned. And I wanted to go faster. Yes?
Hi, I was just wondering if you could explain one more time maybe the input properties parameter and why we had to specify the band.
Yep. So if you open up over here in your console the feature that we printed and you look at it, you'll see that it has B1, B2, B3, all the way up to B9, and a class property. And those came straight out of the image. And sample regions did some smart stuff for you to fill in input properties, saying, here are all the input properties that came from the image. But what we did after that is we fiddled with the features by giving it another property. And so instead of 13 properties, there's now 14 properties. And train goes, hey, wait a minute, I'm only expecting 13 properties. What's going on? And so we need to explicitly say, no, don't classify on that random column. That is not good. Here are the actual properties that we care about, and they happen to be the same as the band names from the composite.
So if you wanted to go back and add another column that you did want to train on, you'd have to do it before the training?
Yes, yes. You're killing me here. OK, so I mentioned if your polygons are too big, we're going to end up waiting. Maybe I'll go make my polygons smaller here.
We're getting a user memory limit exceeded. Should we wait for that? Or?
No, it's a good time. I was waiting for someone to hit it, so that's great. That is similar to the same problem I'm having. I'm just not running out of memory. But 1 second, and I'll talk about that. Anybody else get memory limit exceeded? 1, 2? OK. I'm going to give it 60 more seconds, and then we'll go to plan B. Time's running out. Yep.
Error computation time down.
Yeah, so I'm about to get that in just a second as well. A little of that is 70 of us doing the exact same thing at the exact same time. There's only a limited number of classification servers on our system. And so when we're not all doing it right at the same time, this usually averages out, and you're less likely to hit that. But you can still hit it. How many points were you using?
29,000.
Oh, that's not bad. That should have worked. We'll talk about that in just a second.
An accuracy of 1 means 1% or
100, 1.0, 100%. Did you get that for the validation for the holdout?
Yeah.
Okay. All right, so I got it timed out. At this point, kind of everybody should be timing out, or they should have an answer. If you got 100%, you probably are not using the reduced training. You're probably putting all of the training back into the classifier. So just kind of check that you're really getting the subsets there. All right, so a couple problems that can occur, all occur right here, right now. I was hoping somebody would get the other one. Actually, there's two more. Earth engine capacity exceeded is the one I hate the most because that means we didn't have enough computers. That's literally what that means. And there's not much I can do about that one. There's an out-of-memory error, an out-of-time error, and the other one will be request too large. So all of those sort of mean the same thing. Now we get to learn about how Earth Engine works under the covers in a little more detail. Everything Earth Engine does works in tiles. We're sampling from an image. That means we're sampling from tiles. The default tile is a megapixel, so 1,000 by 1,000, so 1,000,000 pixels. And when we're sampling, that 1,000,000 by 1,000,000 pixels has a bunch of bands. In this case, 13 bands, and they are 13 double bands, high precision floating point doubles. So 13 bands times 8 bytes times 1,000,000 pixels is sometimes too much memory. And the way you get around that is a dumb thing that you sometimes have to do. Up here, if you hit out of memory, you are almost always hitting a tile that's too big. And the way you fix that is by specifying a smaller tile. So tile scale is a thing I made my guys put in 5 years ago as a short-term stopgap for we can't figure out what the right size tile is. 5 years later, we're still using it, but at least it's there. It's sort of an escape hatch for when the system is trying to use too much memory. You can just say, use less memory. Use a smaller tile. Tile scale cuts the tile by that much. And the number can go from 1 to 16. The downside of using it is that if you put in 16, your computation takes 256 times longer to compute because we've cut your tiles down by a factor of 16, 16 by 16, and we've divvied this out across 256 more machines, and there's a maximum amount that can go out, et cetera, et cetera. It just takes longer. So you're trading time for space, and sometimes you run out of time before you run out of space. So for your memory limit error, try a tile scale of, I'd try 4 actually, and see if it works. For those of us that timed out, clearly adding more time from time scale is not going to get us there. So this gets tricky. The interactive code editor, the code editor here, gives you 5 minutes and then it shuts down your computation because you might have specified a computation that's going to run forever, and the interactive environment is not a place to be running computations that run forever. So you have a couple options. The thing I'm about to type isn't a thing I normally cover in the intermediate class. This is an advanced thing. If you don't want to type it, that's fine. I'm just going to show you how I would work around this error. What's actually taking a really long time here is classifying my table. The classifier got built. I can use it. I've seen the confusion matrix. It's all ready to go. It's just running this table that's the tricky part. So instead of classifying my table, what I'm actually going to do is I'm going to go and make the whole classified image and sample from that. And for long reasons that are not important, that's faster. It is faster to go do the entire image and pull out a few pixels than it is to just try and classify a table. So the way we're going to do that, and we're going to want to see this result anyway, so it's fine. We're going to take our composite. We're going to classify it with our classifier. And then our validation data, we're going to just resample. We just want all this stuff again.
No.
Yes?
At this point, it's not necessary to bound the composite to a
Nope.
specific area.
It only does what it needs to do. So I'm going to take my tile scale out because I didn't need it, and it will just make it slower. Yep, and then we will get an error matrix off of the validation. And I hope that works. We'll give it a second, we'll see. So I sampled, I drew my geometries, I sampled points from all those geometries and made a whole bunch of covariates, and I used some of them. And the other ones, I'm actually just going to throw away those covariates and go get the sampled value out of the classified image instead. So I'm really, here validation is only using the same points. It's not using the covariates anymore. And like I said, this is sort of an advanced topic. If you don't understand what just happened, don't worry about it. But this sample regions should run faster than the table classification, and it may still time out. Unfortunately, this is the other part of the system that is goofy. If you want to do really big table operations, sometimes the only place you can do them is in batch. You start a task, you let the task run. You know, this might actually take 10 minutes, and you don't get 10 minutes, you only get 5. And so you need to start a long-running task that will actually have 10 minutes to finish, and it's horrible and terrible, I'm sorry, but that's just the way it works until we can make it better. Anybody else get any of the other errors? There's nothing you can do about memory capacity exceeded. Request too large, right? So you'll hit this one sooner or later. So we take all these tiles, we sample all these things, we make our table of training data, we ship the training data off to our classification service. If that thing that you're shipping off to the service is too big, if it's bigger than 82 meg, it'll fail. Sorry. If you happen to send an 81 meg file or an 81 meg table off to the learning service and you've given it poorly built data, for instance, if you just generated a bunch of random numbers and said, build a classifier, what you're going to end up with is a whole bunch of really, really, really deep trees, because it's trying to find the impurity scores. You know, you end up with a set of really deep trees. And if you're doing random forest, you might end up with 100 or 1,000 really deep trees. And so the thing that comes back from the classifier system can also be too big. You can actually make a classifier that's too big for the system to use. In fact, Nick did this like yesterday. So there's this little tiny pipe between this giant Earth Engine system and our classification system, and things just have to fit through that pipe. So request too large means one of those two things. And either you need to prune down your training tree, or you need to make prune down your training table, or you need to make your classifier not so deep. And there's parameters on the classifiers that will let you do that. So random forest, for instance, there is a minimum leaf population. If you let the minimum leaf population go to 1, like I can build the tree until every single node covers exactly one of my training points. That's going to be a really big tree. And if your data is not well conditioned, that's what you're going to get. So you can say, no, don't do that. Stop if you have less than 10 points per end leaf. Same thing for cart. You can say, don't build more than 13 levels of tree. Stop there.
If you don't specify the minimum leaf population, it defaults to 1?
That is it says it defaults to 1, but you are unlikely to get single node leaves if you have well conditioned, right? It doesn't run till everything fits into one leaf. It's just it won't go less than that. Okay? So those are all the errors you should hit or shouldn't hit. Those are all the errors you're likely to hit. My validation finally finished, and this time I have a 99.7% accuracy. And what you should take away from that is that this particular type of holdout validation is also not good. I took a bunch of pixels that were right next to each other, which I have already said are homogeneous. here's a bunch of homogeneous urban pixels in the same city. I should expect them all to look exactly the same because that's why I drew that polygon. Here's a bunch of water pixels that are all the same. That's why I drew that water polygon. So taking a subset of this particular data is just asking for trouble. You are misleading yourself with this accuracy. I taught this class, like I said, 42 times this year. This is the 42nd one. I stopped right here, or actually I stopped 3 minutes ago in 41 of them. And someone pointed out to me that I'm doing a bad thing, right? This random sampling sounds like the right thing to do, and if my data was in fact independent, it is the right thing to do. If I've gone out in the field and collected a bunch of training data, that's the way to do it. But I didn't. I drew a polygon of a whole bunch of pixels that are exactly the same as each other, and I got this ridiculously high accuracy. And he says, well, humor me, go do it my way. So that's what we're going to do next, is we're going to go do validation data a different way. And we're going to see this accuracy drop dramatically, and that's going to be a much more likely accuracy number. So what we're going to do is we drew this veg up here, this urban here, and this water here. Go somewhere else. Move to another city. Like, say, how about New York? Is there any veg in New York? Philadelphia. They grow stuff around Philadelphia. That's great. And now we're going to do the same thing we just did from scratch again. Make 3 more classes. Urban 2. Water 2. No, this one's veg 2, isn't it? Veg 2. No, more green. Unfortunately, we have to do those other steps that I just skipped. Make sure I got that right. Class 0, class 1, class 2. Okay? Yeah. And now drop some polygons. And you can make these relatively small because you don't need nearly as much data. Although even this data is going to be a little more homogeneous than you might like. Oops. It's all right. And so once you've got some new validation data, just stick it in as the collection in this second sample. So we're sampling from somewhere else. And massive drop in accuracy. And I still wouldn't believe this number because all of my Philadelphia pixels come from downtown Philadelphia. They're still pretty homogeneous there. And like I said, make these polygons relatively small. You don't need 1 million pixels here. You want, 1,000. Who's got a second accuracy? No one yet. Okay. When you get one, yell it out. Let me know. And more importantly, tell me how much it went down. Your second accuracy is 0.999? No way.
Hi, something from Philly.
All right, shall we get started again? Good.
I don't know why my palette is not working.
P-A-L-E-1L, not 2.
Spell check. Thanks.
Oops, that doesn't work. Okay, ready? Let me close this door. So if you want a link to that script, there it is. If you don't want it, or if you did it all, that's fine. If you had trouble, there's a link to the script that we were working with up there at the top.
That's the link, not this.
Well, it is the bottom one, but this is the short version. Okay, TAC, capital W, lowercase y, capital Q. All right, and Michael has it in case you need it. So that was clearly a toy exercise. I really just wanted you to see how to make those feature collections, how to drop points, that sort of stuff. We're going to try and do something a little more interesting now. And what we're going to do next is try to do a crop classification. Who has done crop classifications before? Is it easy? Yeah, it's really hard. Crops from surface reflectance is tough because plants look like plants. So we're going to try to tease out a few ways that we might make this work. I am perhaps going to teach you some bad science, so don't go publish a paper based on the techniques we're about to do. Use some real techniques. These are just some ways to get there along the way. I am going to undo a whole bunch of this script because what I want to do is I want to start with my Sentinel-2 median composite, but I don't care about anything else after that. So I'm actually going to remove it, and I suggest that you save and remove as well because this script is going to get long and ugly. So if you end up with a lot of stuff in here, you're going to confuse yourself. So go back to a composite made from the Sentinel-2 collection. You might want to leave in the map add layer, just because we'll want to see it maybe, but get rid of the rest. Okay? So we're back to an annual median composite, which is a terrible place to start, except for all the other places to start. So what we're going to do now is we're going to go get some training data from somewhere else. We're not going to draw our own training data. We're going to go get someone else's training data. And what we're going to go get is the crop data layer from the USDA. And we'll use their idea of what crops are to build a classifier so we can build our own crop type. The CDL is in the data catalog. There it is. So I'm going to bring in the collection ID. You can import this if you want, but we're about to do something else with it, so I don't recommend that. So go and get the collection ID. And we will bring it into our script. As an image. It's actually an image collection, but I just want one image out of it. And that's the 2016 image. Oh, I also don't care about all these geometries. I'm going to get rid of all my geometries as well. I'll come right back for you guys. I just don't want them on my screen. Okay? And a thing I do that is a debugging technique, but really it's just so I don't ever have to have a debugging for this. When I get something, regardless of what it is, I stick it on the map. And if it doesn't look like I expect, then something's going on. And that does not look like I expect. Crop data layer is this discrete colorized thing, and that is not that. So if we inspect it, we can see that there are, in fact, 3 bands in the CDL, not 1. And we didn't want 3 bands, we just want 1. And we want the cropland band. So we will select cropland. There's a confidence layer, which is a percentage of how confident they are of that value. We could use that as guidance for the classifier, but that's more detailed than I want to get right now. And then there's a binary, is it cultivated or not? We could also use that as guidance for the classifier, but I don't want to do that right now either. So that looks a lot more like cropland to me. The CDL has 240 classes in it. And it's going to be, crop type is hard with 2 classes. It's going to be really hard with 240 classes. So the nice thing about it is it's sorted by frequency. So the lower numbers occur more often. So I'm actually going to suggest that we're going to make a crop type map for the first 10 classes, which actually means the first 6 classes because they don't use 7, 8, and 9. So classes 1 through 6. So I want to get rid of all the other classes in this layer, and we will do that with a mask. So everywhere that the value is less than 10, we keep. Everywhere else, we get rid of. And we'll go back to, I thought I saw a lot of stuff in Delaware. We're going to go do this in Delaware.
Question.
Yep.
So how you selected 10? In case you don't know that, can you print a histogram of what values exist?
Yeah, exactly. We did that a minute ago with our class type. You just arrived, so you didn't see that. There's 3 prints in a row. One of them is a histogram of crop type classes.
Is there anything meaningful about the first 10? Or just random?
They're the most popular. They're the most commonly grown ones. So corn, rice, soybean, sunflower. I don't remember the other 2. All right. So now we've got some supervised data. We have our covariates in our composite. We still need to extract them into a table. So we've already seen that happen. Instead of drawing a bunch of polygons all over the place, I'm going to draw a polygon on Delaware. Because it looks like Delaware is pretty much crop. And then we're going to sample it. This time, though, we're going to do a stratified sample. And we want 1,000 points per class. And the class band is called cropland. And we just made a region. If you didn't go and delete all your geometries, there's no telling which feature collection you just put that geometry in. So it's time to clean up your geometries. And we'll do a 20-meter scale. And right now, I don't care about the rest. Oh, I forgot one step. I've got my composite, but I need to add my cropland band to that thing so I can sample it. Now it'll work. This will take a minute, and if it takes too long, we will make our polygon smaller so we don't all have to wait. But we'll see how long it takes here. I hate that one. So you probably have put several geometries together into into a feature collection. Memory exceeded. Anybody else get memory capacity exceeded? Yeah, let's. I have a feeling this isn't us. I have a feeling someone is currently not in this room doing something rather crazy with the system because it's happening very fast. But we will just start debugging and see if we can make it better. So I'm going to make my polygon smaller. See what that does. All right, that looks like it's working. So if we were doing something, if we were trying to get to a publication, if we were trying to do a long workflow that was going to take more than 5 minutes, I would just run this as an export and get the thing generated as an export. But we don't want to do that right now. We want to just get something interactive. So a couple things I tried was making my polygon smaller, making my scale larger, and those seem to work. So it really does mean it's a memory limit problem. So I actually just turned my composite into a bunch of floats instead of doubles. That cuts my size in half. It uses less memory. That seems to be working. I realized that was a really fuzzy debugging guide, but it's a really fuzzy system. Yeah? Parallel processing systems are tricky to debug in the best of cases. All I have is some tricks and tips to help. Anybody get a size finally? Just me? Oops. How many points you got? 203? 2,000 and a little more than 2,000. Okay. Anybody else? Well, at least it's computing.
3,000.
Exactly?
Exactly.
Okay. How many? Okay, we'll give everybody just a few more seconds to get some numbers here. How big's your polygon? For now, bump your scale to 50. 50.
Just to catch up. So what exactly are we counting here?
This is the number of pixels that were extracted from this region that have a classified, a supervision class, yeah, a label. Correct. So the thing I'm sampling are my covariates and my class band. So it's making all 13 band properties and the class property. It's pulling them all out at the same time. And if you print one of those, that's what it'll look like. Just like before. Print training.first and training dot. So there's my features. As you can see, all the covariates and a cropland band. And I went ahead and printed my histogram so I can see what's going on with this weird number. You were asking for 1,000 points per class, and you got 3,013 or 2,008 or something. And that's a weird number to get. So if you don't get exactly what you were expecting, you should maybe investigate. And the investigation I'm doing here is, again, my frequency histogram of the classes. And I can see that in this region, I've got 2 pixels of class 6. Whatever class 6 is, it's not growing much in this area, or it may even just be error, right? The CDL may be wrong by those 2 pixels. We can leave them in, but again, if I was trying for science here, I would remove those 2 pixels and continue forward.
I got a null histogram. It says null 3000.
Did you maybe...
Oh,
You missed a step.
So my histogram, I have exactly 1,000 of 2 classes. Does it stop counting at 1,000?
Yeah, stratified sample, number of points is, I want 1,000 points per class. There's more options on stratified sample. If you want 1,000 from one class and 5,000 from another class and whatnot, there's more options in there to let you do that. But yes, it stops at the number you tell it. Yep. Everybody have some training data? Anybody still spinning? Waiting? Errors? Spinning? OK. We'll give you a second.
What exactly does the tile scale do?
Tile scale makes the back end use smaller chunks. That's all. But it has to then process more of them, so it takes longer. And it tends to reduce the memory usage.
It's not the Landsat column, the Sentinel column.
Yeah. It's a thing you shouldn't even ever have to see. We just haven't gotten around to doing it for you automatically. Still spinning? Anybody? One?
I got a tile scale of 16 and
Well, the higher that number, the longer it takes. Try 2. If you can get away with 2, if you can get away with none, that's great. But try 2 if it doesn't work.
I got it done.
Okay. All right. So once again, we've got a training table. It has covariates. It has classes. We're ready to do some very bad accuracy assessments. Rather than even bothering with the resubstitution error, let's jump straight to holdout the same way we did a second ago, the same way we did the better way a second ago. Let's draw another geometry for holdout. And we will take this block here and do it again. Oh, wait, no, let's, we're going to skip the table step. We're going to sample from the image instead, which means we need an image. We need a classifier. All right, let's make our classifier. Skipped a whole bunch of, several steps in the wrong order there. Build and train the classifier, apply the classifier to the image, stick the image on a map just to sort of see when it's all done. And then for validation, we're going to sample in our other polygon for some validation points. Even bigger than I care about. Let's do that. One of the nice things about doing the sampling with stratified sample is that the points are not right next to each other. When we were doing sample regions, if there's one farm of corn, we were getting all the pixels from that farm, and you would expect those pixels to be exactly the same. And so for validation pixels, they're not, there's no homogeneity, or there's no heterogeneity. With stratified sample, at least the points are coming from different locations. We still want to do it in the other polygon, though. Say again? I did draw a second geometry in the wrong order. I apologize.
Can you explain a little more what stratified sample
No. Stratified sampling is taking some number of points per class. And so you need to specify what the classes are. That's what's going on here, which band has the classes. And then for every one of those classes, it will go and try to get this many points randomly located in the region.
What is the tile scale?
Tile scale is how you tell us to use less memory in case it breaks. Right here, for this one, it's actually probably not necessary, and it just makes it slower. So let's see if we need it or not. And I told you I would tell you what geometry's true means while I'm waiting. I guess now is a good time. By default, when we sample points out of an image, we don't assign a latitude and longitude to that point because it takes more memory. So you can turn that off and on with this relatively new feature. If you really want to see your points on the map, you can tell it to add the geometries into the points, and then they're normal points, and you can display them on the map. I haven't actually stuck on any of my points on the map, so this is just taking memory. I could omit it if I was hitting memory limits. Churn, 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 wait, wait, wait. Anybody finish? Nope. Okay. Me neither. I'm tired of waiting. I'm going to make my polygon thinner.
The number of zero.
Where?
Validation.
A validation of 0? An accuracy of 0?
The accuracy is showing up as 0.
You probably got one of these misspelled. It means that you're comparing properties that don't exist, probably. Num points missing 2. So you misspelled num points. Did I get it? Normally this actually runs faster. I know that sounds like an apology. It is an apology. Earth Engine is designed to handle thousands of users doing different things, not a bunch of users doing the same thing. So we're breaking it. Come on. All right, I'm going to go for a lower scale, so it will go faster. Yep.
So would that be different if you're doing different places? You said it's not designed for the same people, but a number of users.
No, the location doesn't matter so much. It's the fact that we're all hitting the learning service with a big table of about the same size at exactly the same time. Yep. It is a little bit, we are all hitting exactly the same Sentinel-2 tiles, and so some pieces of the system are really hot right now, but usually that handles that pretty well. This is the learning service all being hit at the exact same time. Yep. All right, mine finished, finally. Anybody else finish? What's your accuracy? 59%. 46%. 38%. What did I at least get? I got 53. Am I the winner? No, 59. Someone's got 59. 56. How much? Okay. So as I started off, crop type's hard, right? Especially with this one image for the whole year, not even turned into NDVI, right? We're just classifying straight on top of reflectance. And so, you know, it's green is green, and you don't really know when the pixels are from. Anybody still spinning? OK, I'll stall for a minute or two longer. If you're tired of waiting, you can go ahead and bump your scale up to a larger number, and it will just use a lot less pixels and not be too inaccurate. The only important part here is that whatever scale we end up with right now, that's what we're going to compare against later. So at 50 meter pixels, I got 53% accuracy. When I check validation in a minute with whatever improvements we make, I need to use the same size pixels so I know that I'm doing the same size. I'm comparing apples to apples. Or corn to corn, comparing corn to corn. You don't have to. For a little bit of scientific rigor, you might want these two scales to be the same. in fact, doing some kind of like crop classification on averaged pixels is pretty questionable all around. But yeah, at least you'd want them to match perhaps. Still spinning? Anybody? 1, 2, 3, 4. All right, you get 70 more seconds.
42%.
No.
0.42.
42, okay.
Can you quickly summarize what is that interpretation, that 53% again?
53% of the pixels in here were classified with the same result that the CDL started with. All right, you ready to move on? Here we go. So the rest of the day is trying to get this number higher. That's all we're doing is we've got a non-toy application. It's still a little simple, but a non-toy application. And all we want to do next is make that number go as high as we possibly can without cheating. So one thing we might do is we might increase the number of trees. Another thing we might do is increase the number of points. Another thing we might do is put other stuff into our feature vector. So I'm going to start with number of trees, which with this many people and the learning services already being overloaded is going to be an interesting exercise. But rather than guessing what number of trees to use, I'm just going to try all of the answers. And this sounds flippant. It was intentionally to sound flippant. But what we're going to do is we're going to try 10 trees, 20 trees, 30 trees, 40 trees, 50 trees, 60 trees, and see which of those comes out best. Because how many trees is a little bit of a black art. You might be able to figure out a good answer empirically, but really, you won't. So I'm going to show you how to do some kind of parameter tuning, like the number of trees, all at once. You could do this 10 times. Some of you might have already tried to do this and done it 10 times. Shame on you. The right way to do this is to map over the number of trees. So it's been a little while since I've done this, but I think we want to start here and make a function. Over trees. And we can't print, but we can do this. So what this function does is it takes a number, and it does everything we just did using that number for how many trees to put in the random forest. And unfortunately, we can't add our result in the forest, in the map, and we don't need to do the classification. Do we? Wait, yes, we do. Okay, we need those steps. And we want to move our error matrix accuracy result into the function as well. So, some fiddly stuff. Okay. When trees is 100, make 100 random forests, classify our composite with it, sample, computer an error matrix, and return it. And now we want to do this a bunch of times. What could possibly go wrong? I want to go from 10 to 100 by tens. And I want to apply my function to that list. Accuracies, did I spell that right? We'll just call it or accuracies. And if I get there before you, it might actually finish. So I took all the stuff that is dependent on the number of trees, and I stuck it in a function. And that function takes the number of trees to use.
Why?
Because I want to call this function 10 times with different numbers of trees. I'm trying to optimize or figure out how many trees do I really need with this number of covariates.
You initially used 20, right?
I did. I just guessed.
You guessed
Yeah.
20. Now you want to range between 0 to n.
Yep.
And what is n? Like,
It will be one of 10, 20, 30, 40, 50, 60, 70, 80, 100, because this is what I'm going to plug into that spot.
How about instead of from 1 to 10, different combinations, like random? So to select the one can give us a good accuracy.
You could try to do that, but I don't think it's valuable. The number of trees is going to plateau pretty smoothly. So a stochastic sampling isn't going to help you much. You just want to know where does that number plateau, and you can stop after that. It may be that we really need 1,000 trees, and I don't really want to try and wait for 1,000 trees, but random sampling in that is not, random sampling for number of trees is probably not going to help us. There's other places where it might, but not here. So the first one took, for me, about 45 seconds. This might actually take about 4 minutes. We'll let it run, and we'll see what happens. It may not finish. Again, this might be a thing that you need to do as an export, because it might take 6 minutes, not 4 minutes.
like accuracy, can we measure other metrics such as precision or recall?
Yeah, those are consumers' accuracy and producers' accuracy inside the confusion matrix, so you can access them there. If you're tired of waiting, make a much smaller polygon, it'll go faster. And your original accuracy number is going to get recomputed, right? 20 is one of these trees, so you'll be able to actually have a fair comparison here still. Then you forgot to put n here. You're using the same number of trees in your forest each time. And in fact, if you got the exact same number, that's possible. You're using the same 20 trees every single time.
Could you do an example with setting the leaf population size, like what that would do to the random forest classifier?
We'll have time to do that, but you do it exactly the same way, and the accuracy is just going to get worse as you make that number higher. I think there might be a depth setting as well. Certainly on cart, there's a depth setting. I'm not sure on random forest. All right, I'm getting bored with this one. How about you guys?
So what if I get the list with all the same numbers?
Excuse me?
If I get a list with all the same numbers?
Then you didn't put, you got a list? Oh, yeah. So you forgot to do this. You're using the same trees each time.
So I got results, I just don't know how to read this list.
So it is, the first number is 10 trees, the second number is 20 trees, the third number is 30 trees.
Okay.
So what happened?
For 0, it's 0.66. For 1, it's 0.67. For 2, it's 0.69. They're all between 0.66 and 0.69 all the way through they're 9.
Okay, so you plateaued after about 20 trees. Hey, that was a good number. And more trees doesn't help, right? In this particular case, a lot more trees didn't help you.
Yeah, it's within 1% variance.
Right. And really, if the number goes down, like if as you add more trees, the number goes down at all, that's your noise. And you should expect about 1% noise. So don't believe numbers to an accuracy better than 1%.
So I got the 97% for all of them.
They're all exactly the same. So if you're getting the same accuracy, that means you're using the same trees, and you forgot to do this bit here.
So, other than computationally making a lot of sense to try to get the number and certain number of trees, like in terms of the classification, does it matter?
I'm sorry?
So other than being like, in terms of computing, it makes a lot of sense to try to get a specific number of trees that we want around the classification. But for the purposes of the classification itself and the accuracy, does it matter to be that precise with the number of trees we want to use?
No, but you want some indicator. Like if we were doing, if you plotted this curve out and started with 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you're going to see a big accuracy difference there. 10 was already pretty high on the slope, and 20 is near the plateau. So because we don't have that many covariates, we were already over guessing on the number of trees to begin with. We're about to add a whole lot more covariates. So if this finishes. Since it actually worked for somebody, we may continue, because it may take a little while to run. Mostly I wanted to show you the technique, and if you're running and getting a list, then you have the technique. You have the pieces you need to make that work. And someone found for us the important number here is 20, right? 100 doesn't help. That's just a lot more computation that you didn't need to do. Go faster. We'll give it 60 more seconds. Anybody else get a list? Everybody else has big polygons too? This is being recorded.
I would have dressed a little nicer.
You can't dress nicer than an Earth Engine t-shirt. All right, I'm about ready to cheat. Same options, smaller polygon, tile scale, increase your scale, one of those. You shouldn't hit that error in an export. And really for these big kind of tasks, an export's a better job, a better way to do it. So when you hit that, you might try again once. If it doesn't work, then we just jump to trying to export the numbers instead. Yeah, me too. What did I get? Timeout? Timed out. Control space inside the paren, or yeah, inside the paren. Alrighty, so that exercise didn't go quite as planned, but someone got it to work, and the answer that we were looking for is 20 trees is fine. So we're going to cheat, and we're going to go back to 20 trees and try something else to improve our accuracy. The total accuracy change over 10 to 100 trees was less than 3%. So that is not going to help us, right? There's no way we're going to eke our way up that way. So we need plan B. This is a good point to save because I'm going to undo that function. But you might want to keep that function for later purposes. I'm going to go back to exactly 20 trees. And there's probably a 20% chance I'll just make that function again in a minute. But so what's plan B? Plan B is either more covariates of some variety, or what was the other option? Oh, more points. We're already having trouble with the number of points, and it might help a little bit. But I'm going to jump straight to the punchline, which is this median composite is 1 pixel from the year, and that's not a good choice. That's not how you map crop type. You want to bring in phenology. You want, corn greens up different than wheat. If you can get samples from different times of year, then you can teach the classifier about phenology, and maybe it will do better. So that's what we're going to do. Instead of 1 composite for the whole year, I want to make 4 composites for 4 seasons. And if we had enough data, we could actually make 1 composite per month. And then things should work pretty well. Sentinel-2 doesn't collect all that much data in the US, which is where we have this training data. And so we have to make a trade-off between data availability and the training data. If we had better training data somewhere else, then we could do that. So what we're going to do is we're going to make seasonal composites. So we're going to break our script for a minute, but then we'll fix it. So up here at the top, where we make our composite, we're just doing this big median. Let's do something else. Instead of that, let's make something to represent our seasons. And those are just going to be the number of the month of the start of the season. So we'll start in January, and we will go to December, and we will step by 3 months. So this is just a list of the numbers 1, 4, 7, and 10. That's all that's going to make. 1 to 12 by 3.
Can you start from 12 December? Because in the spring it's better to include December, January, and February.
Yes, but it's harder. Go with me for a minute. I'll show you. Just making the numbers. All right, so those are the months we're going to work with. Now we're going to map a function over that. And what that function is going to do is filter our collection to just those months and then take a median. I'm about to type something that will cause you problems. What we'd like to say is filter on month from whatever month we're given to whatever month we're given plus 2. But if you remember from yesterday, no pluses. Not allowed on computed objects. So we have to do something silly here. What I just did is called casting. I think I mentioned it yesterday, but I might not have. I have to tell the system what month is. I have to remind it, hey, that's a number. And once it's reminded, it will say, oh, that thing has a function on it called add, and now you can have access to add. So you had to cast it to a number just to get to the add function. So let's print our seasons to see what we got. It's the list at the top. Oh, I always make this mistake, and it always takes a long time here. We are going to filter this so that we're not trying to process all of the Copernicus images everywhere. We're going to process this down to our geometry, buffered by, let's say, 50 kilometers. Otherwise, it'll take a very, very, very long time.
Is there a way to run on the section of the code?
No, because you're not actually running any code here. You're building a computational description and sending the description off to the server. And the server needs the whole description. So you can't just run a piece. You can comment out pieces and run them that way, but that's the best you can do. Everybody get a list of images? Yep. Question?
When you put a number and it assumes it's meters, is that tied to the integer, or is that just something always?
Scale is always meters. Which number are you talking about? Oh, for buffer? Yeah, no, it's always meters. All right, anybody not have 4 images yet? Okay, we'll give you a second. If you're spinning, you didn't do this step. I stuck this step in to reduce the total number of images we're processing. It should finish in 1/10 of a second. Or at least the first part should finish in 1/10 of a second.
Could I get a memory exceeded error message? Is it because
Down later,
collection?
here. Where at?
I think it's on the list.
This one?
Oh, it's beyond this.
So you already got the number, you got the feature, you got the object. Capacity exceeded or user memory limit?
It's memory capacity.
Yeah, that's not really you. You're using a lot, and that's not helping, but I think that's everybody. Just try running again.
Okay.
Anybody else still spinning? Still waiting on a list? Nope. Sure. What we just did is we made 4 images, one for each season. Now we can just take those images and stick them into our composite as a bunch more bands. So we go from being a 13-band composite to being a 56-band composite. And there's a pretty simple way to do that. And I don't want to wait, so I'll get that right back for you, but my polygon is too big. I don't want to wait. I don't care about that anymore either. So I had to comment out the layer where I'm adding the composite because my band names all changed because I've got 4 copies of every band now. 4 red bands, 4 green bands, 4 blue bands. And so my band names changed. I didn't want to fiddle with it. So just comment out displaying the composite. And we'll see what happens. My one feature, my first feature that I'm printing, there's all my covariates, all 32 of them. How many? 53. All 53 of my covariates.
So here you made one image with all these bands in one,
Yep. Take all 4 images,
and all their bands.
turn them into an image collection, and turn that whole collection into one image with a bunch of bands. So 53 bands, 56
one
bands
image.
in one image. Yeah. So the question is, do you get different amounts of processing interactively versus in batch? And the answer is they are very difficult to compare. Interactively, you're sharing with everybody else. You get a 4.5-minute limit, and the number of computers is really hard to pin down. In batch, you basically get 100 computers, and they're all yours. We have I think we have about 1,000 machines for the interactive stuff, and so that's 1,000 spread over 70 people, and that's why everybody doing the exact same thing at the exact same time is such a problem. Whereas in batch, you get 100 machines, and they're yours. All right, so that was a little bit disappointing as an example, but at least you know how to do it. Are there any questions? Not even, so, yeah? You want to see more code? To export? Okay. All right, so I'm going to let my export run for a minute longer here. Actually, it'll just keep running, and I don't have to wait on it. Yeah?
Just one question about classifier. Once you trained with certain data, I would assume it had the memory of, for instance, what forest should look like. But I could not use, I always have to use within the study.
No. You can build a classifier in Brazil and run it in Indonesia, and it's fine. Once it's built, it will work on anything with the same named properties, and it doesn't care where those come from. Will it work? It'll be a terrible classifier maybe, but you can certainly do it and see how it works.
Do you have any examples here or link?
Well, we kind of are doing this already. If we look at our result, it exceeds our study area by a significant amount.
So if I replace a new study area, it should still work as long as the class properties are.
Yeah. So, I don't have my study areas over there. I'm classifying over here. It doesn't matter that this is only 100 kilometers away. This will work globally. Okay. It's an ugly. I didn't stretch it, so it's an ugly image. But all right. So my task is still running. It will keep running. Pretend that worked, and we'll go forward. The next thing I want to show you is sensor fusion. And this works almost exactly the same way. What we're going to do next is we're going to go make some Sentinel-1 composites and stick them in our feature vector and see what it does to our classification accuracy. Or maybe one of us is going to see what it does to our classification accuracy. But again, I want to show you the technique. Make your polygon smaller just to get through it, and then you can do it in a big batch when you want to do it. Okay? Yep. Where I make the composite. All right. He's debugging. I'll give him just a second. Oh, it looks like actually maybe this finished. Yeah, my other one finished. Let's see what that accuracy was. 72% at full-size pixels. So, again, I went up from 54 to 72. I like that number. There it is, 72%. Right, so the export finished, the classifier's cached, and now I can just use it. As long as I don't change my inputs, it will reuse the same classifier, and I don't have to wait for it to train and build and all that stuff again. Okay, Sentinel-1. Who uses Sentinel-1? Anybody? Who has no idea what Sentinel-1 is? little bit? Okay, we'll go through it real quick. Sentinel-2 is an optical instrument. Sentinel-1 is an active microwave instrument, synthetic aperture radar. It's a microwave that looks out the side. It blasts out a big microwave burst. It goes in a polarized microwave burst. That's a thing you can do with microwaves. The polarization, the polarized wave hits the ground, bounces around, scatters, changes polarization, and comes back. And they do this fast, but they do it in bursts. And then they collect all that data together, process it with Fourier transforms and whatnot, and they make a backscatter image. What happened to the, how well did the microwaves scatter once they got down there? They bounce off of water or they're absorbed by water, I don't remember which. They bounce really well off of buildings, and so there's a really bright return for buildings. And then trees and veg and roads and bear all treated differently. Sometimes the microwave turns and comes back with a different polarization. And then to complicate things, it's a side-looking instrument. So as it flies south to north, it's looking east. And as it flies north to south over the backside of the planet at night, it's looking west. And so you get different shadows depending on whether you're flying up or down. But the good news is it runs during day and night more or less equally, and is basically not blocked by shadow, or by clouds. So it's a fun instrument in places that are cloudy because you don't have to worry about clouds. But all of that complication means that the data is a little finicky to get going and start using. And it's finicky enough that we have a how-to built into the user's guide to tell you how to get started. So if we look for Sentinel-1, that's the SAR GRD, open up that data set description, and at the bottom of the text, there's this Sentinel-1 preprocessing article. Open that in a new tab. Okay, search for Sentinel-1, click on the data set description, at the bottom of the text, get the preprocessing article. And in that article, here's some code. Just like our how to mask clouds code, this is a great place to start for how to do something with some Sentinel-1 data. So we're going to cut and paste everything down to here into our script. So the first 3 paragraphs of that chunk of code, cut and paste into your script. And we're going to paste it in just above where we're making the composite. Right after seasons, right before composite. And what this really does is it keeps you from having to type these really long metadata names because we'll all mistype those and we'll be here forever trying to debug that. So if you cut and paste it, which polarizations you're getting is already set. Which of the many instrument modes they're using is already set. Whether you want ascending or descending is already set. And then we pick either ascending or descending. You generally don't want to mix them because, like I said, the shadows go one way in ascending and the other way in descending. So the brightness changes on things depending on which one you're using. It doesn't really matter which one, except where you're located. They don't collect a whole lot of data in the US. Some of it's ascending, some of it's descending. I don't really know their scheme. One of these collections has a lot more data in it than the other. So I'm going to guess right now that I want descending data, and if there's not enough data there, we'll go the other one. One more thing, this is the entire Sentinel-1 collection for all years, for all regions. So we want to filter this down the same way we filtered our Sentinel-2 data with a filter bounds and a filter date. So copy this filter date here and copy this filter bounds here. And we should have some usable data. VH descending. let's see what it looks like.
Can you make a short link for people who are...
You bet. One second, we'll come right back. Can you read that? Yeah, you can read that up there at the top. PWJ DXS.
Anyone who's stuck, this is a shortcut. Did you get the link?
Uh-oh, something didn't work. And now we have a problem because I didn't plan ahead. Sentinel-1 didn't exist in 2016, so we're trying to get data that doesn't exist yet. I'm going to bump up by a year and see if that gets me what I need. Is that true? Nope, I've done something wrong. 1 second. I just gave you a link that doesn't work, so give me a second. Filter bound, filter date, polarization, DH. Let's try ascending. There we go. All right, so I told you they don't always collect ascending and descending for the US, and I picked the wrong one. All the data is in the ascending collection, not the descending collection. So we can just throw that one away. And that's what it looks like. Anybody got a map of Sentinel-1 stuff? Oh, I did a bad thing. Okay. Lots of help. Raise your hand if you're having problems. There was lots of fiddling going on there.
Can you take a snapshot of this?
Yeah, let me do that one. There. If you want the link, W4U EY3, lowercase e. Okay. Yep. All the way at the top. Okay.
I just used your link and then tried to run it. It says classification request exceeds size limit.
Totally possible because I changed everything to be 20 meters and ran it as an export.
Okay.
We'll fix that up in a second. Right now we're just worrying about the Sentinel-2 data, or the Sentinel-1 data. Now, does anybody have a Sentinel-1 mosaic? 1, 2, 3, 4, 5, 6. Okay, half of it. Did you go to the link? Yeah. Okay. In all my workshops, I want you to understand everything I do, but I also kind of want to challenge you because there's way more content than I can possibly deliver. So the last hour of every workshop is often just people watching it happen. And if that's you, that's perfectly fine. This is just an idea. I want you to understand that it's actually quite simple to do these quite crazy things. All right, who needs more time? One in the back. Stick your hand back. Go. I'm going to inspect this map so you can see what's in it. It's got 3 bands. The vertical and vertical polarization band and the vertical and horizontal polarization band. This is outgoing polarization and incoming polarization. VV, both vertical. VH, outgoing vertical, incoming horizontal. But it's also got this angle band that has something to do with the incidence angle of the outgoing radiation. I don't care about that band. I want to get rid of it. So I'm going to select, not there, there. Select the VV and VH bands. Don't forget to get rid of the stupid semicolon. And now we've got 2 more bands that we can just stick into our classification. So right here where we make the composite, add bands, VH ascending. I can't type that word. And I'm going to go back to 80 meter pixels so it will run, and we can see what it works out to. And see if it works. Oops, image add bands. That's all right. Hey, welcome to my world. Oh, I added a whole collection. Right, I didn't mosaic this. I have a big giant collection full of Sentinel-1 data. I have to turn it into an image to be able to do this. And unlike optical data, mean is a great operator here. If you've got multiple Sentinel-1 bands, taking the mean of them will actually knock down the noise a little bit. I was debating whether this is a good idea or not because we're actually looking at some seasonality here, or we want to look at some seasonality. But mean will work for now. That's a mean crowd. Y'all laughed at me when I had errors. I didn't laugh at you. All right, it's fair. It's totally fair. So this will run, a number will come out. What do you think? Will the accuracy go up or down with an annual composite of radar data added into the mix? By a lot? By a little?
Maybe
15%? Well, that's a good guess. I mean, that's an optimistic guess. Anybody else have a guess? Oh, yeah. That was 82% a second ago, by the way. 1%. Part of that is I have an entire year's worth of data. So any phenology, anything about that crop is just gotten mushed together.
It was 72 because you changed the scales to 20, right?
Let's find out. I can simply remove it and see. It should be cached. It should be instant. 82. So I went from 82 to
The scale is still at 80.
80. Yeah, both the scales are at 80. I'm trying to compare apples to apples here. So 82 to 83. The percentage went up a little bit. Actually, maybe just in the noise. It may not have helped any at all. And I don't know why. We took the mean. Maybe that wasn't a good choice. We can try the median and see if that helps. Min and max are actually meaningful numbers here in Sentinel land because the min will actually be the pixel with the least speckle and essentially the wettest pixel. The water absorbs the microwaves. The min number out of a sentinel composite is the wettest pixel. That might actually be a little diagnostic for what we're trying to do. I don't know.
Maybe try a different quantiles instead of big quantile median, 75 quantile.
Maybe. Right. So the point here is you get a lot of options. If you want to do percentiles, that's fine. You can do every 10 percentile through the collection stack all at once. So you add 10 bands per input band rather than one. If you want to do, let me rephrase that. There are a lot of people that publish papers in journals like Science, which have been doing this with these kinds of data sets, but not working on the reflectance data directly. They work on perhaps some band indices, and then they don't work directly on the band indices either. They work on the min, max, mean, mode, and median, and maybe standard deviation of those band indices. So you compute maybe NDVI, NDWI, and NDBI, bare index, and then you compute percentiles of those, including min and max, and maybe the median and the variance. And so 3 times 4, 12 bands. And that's what they're classifying on. And you should be at a point right now where you could do that computation pretty trivially, right? You know how to do mins, maxes, means, modes, medians. You know how to do all that stuff. You know how to take the variance, even though you don't know it. You could figure it out. And you just stack those bands together into a feature vector, and then you classify on the feature vector. The limitations for the people that publish those papers in Science then turn into where do you get the high quality training data? And I was just in Colombia working with the Ministry of Environment there, and they said, you know, the technique we use almost doesn't matter. We've tried a whole bunch of techniques. All of them produce an 87% accurate map, give or take, plus or minus 2, 3, 4, 5%. But 87% is not good enough for what they're trying to do. They need 96, 97%. And so they spend months generating high quality, really high quality training data to go into that map, and then they don't really care which of the algorithms they use at that point. So for almost everybody that uses Earth Engine, and we talk about the project and they go, I got these great ideas, the answer is always, you're probably going to end up being data limited. You want high resolution data from the 80s, doesn't exist. You want training data for earthquakes around rice fields in Cambodia, doesn't exist. So you're going to spend all your time generating data, and that's why you get to publish science papers. The tools are now hopefully pretty trivial, minus the whole export step. Sorry about that. But even still, it worked, right? I ran it at 20 meters. It took 2 minutes to export. It was done. So if everything worked right, you've now got the tools. You just turn the crank on them. There's not a whole lot to do with them, and you can do them at really big scales.
No, I changed my CL and Sentinel-2 to match the Sentinel-1 here, and then the accuracy goes up a lot.
Some of those CDLs are better than others. I'm actually still using 2016 all the way through. I thought I didn't have data, but I was wrong. It was the VH versus, it was the ascending versus descending. So but that's an interesting point, that the 2017 data, there's probably a lot more data. They were just ramping up on some of those. And so you might get, a lot more data might give you better accuracy because you have better signal to noise. Questions? Anything you want to see?
So with the data, I'm really curious if there is any plan or anything coming where we could actually automate by segmenting image using some kind of threshold. If you have very few bus, let's say land cover class of 5, wouldn't it be possible to have a start in data instead of manually looking for?
So you mean, I'm going to try to infer what you're saying here. You mean use some unsupervised clustering technique on that data to try to tease out some classes early? Totally possible. If you got the link to the classification slides at the very front, some of those slides are about unsupervised clustering, so k-means and some others. We do those as well. Unfortunately, I picked a bad library when I built all those. So they work, The problem is that they are even more limited than these tools. You will probably not be able to do clustering with more than about 50,000 points. 500, it takes 10 times more memory because the library is a bad library. We're working on replacing that. But there are clustering tools there, so you can at least do something with them and try that out.
But there is I don't think it's integrated, but there is a way of getting the optimized classified thresholding and looking at the intra-class versus inter-class variable concept. Yeah, concept. Yeah, I'm very curious about that.
I haven't seen multi-class OTSU though.
Single class also, right? Are you talking about multiple? I think single class also Nick wrote a tutorial on that.
Yeah, if you're just trying to do forest and non-forest, then yeah, you might be able to do simple histogram thresholding to find the optimal points. If you're trying to do 5 or 6 crop types, I haven't seen anybody try that because I've never seen a multi-class threshold. But yeah, you now have the tools to be able to try it out. I hope.
In terms of the methodology of the analysis, in terms of your twinning and your validation, would it be a better option to just stick with points or do a polygon sampling?
Science. I don't know. I hope I conveyed early that I was going to teach you bad science, right? I'm just pointing out, I'm an engineer. You should not rely on me for deciding what is good science or not good science. You want holdout validation, I made holdout validation. You want resubstitution error, I made resubstitution error. Something probably none of you actually know. I'm in the process of getting my PhD. So in theory, I'm not yet qualified to tell you those things, but I'm working on it. Yeah, you shouldn't be relying on me for science advice unless you're one of my science partners. You should be doing good science and let us build some tools for you. Because Noel said so is not an accurate defense for your reviewer. Not okay. Sure. I showed you this yesterday, but in fleeting passing, and that's a great question. So if I have, let me make sure.
Add to that then, if you have, say, a polygon and it has different types and then exporting what percentage of?
We can do percentage as well. I'm going to get a link for this, which is sort of our finished product here for Sentinel-1 and Sentinel-2 classification, in case you want it, because now I'm going to chop up this script. So if you want it, there it is. IXB ENQ. Lowercase I, lowercase b. Okay. Michael's got it if you need it. 5, 4, 3, 2, 1. Gone. Okay. So I'm going to go back to our result. I don't care about the validation stuff anymore. And what I'm going to do is I'm going to compute inside my polygon area of each of the classes I've got. So result, reduce region, area. We're doing area. Result dot add bands, ee.image dot pixel area dot reduce regions, reduce region, yes. I want to sum area, but I want to group on the first band, the classification band. The region I'm doing this in is my input geometry, 20 meter scale. Don't care, don't care, don't care, don't care. And we will call this areas. Michael, fix this. All right, it's complaining about the order that I've done this, but I don't care about weighted pixels, so I can just unweight them. By default, sum and mean and those reducers use weighted pixels. Pixels that have a partial mask are only partially included. And that's the pixels on the edge of my boundaries and whatnot. There's a limitation that the grouping field has to come after the weighted fields. And rather than switch the order, I just said, don't use weighting, turn it off. And we'll see what I got. Ta-da, see, that one ran fast. Now, if I want to do percentages here, I would just get the total area of the polygon and divide it by each of these, and I'd have percentage weights.
Is this the area where you said it doesn't matter what scale of projection it's
The classification will give you slightly different answers at different scales, so you're going to get slightly different answers. But the pixel area doesn't care. Other questions? This will be in meters squared, yes. And you know that from the pixel area documentation. 1 second. Square meters.
Assuming that we have about, say, 12 or 15 classes, is there some way we can tag those class names back instead of the index of 0, 1?
Yeah. If you think everything's been fiddly so far, let me show you how that works. So the crop data layer has on it names and numbers. So if we print it, it has a property called names, and those are the names in the same order as this other piece of metadata, which is the values. So the crop data layer image has in it 0s, 1s, 2s, 3s, 4s, 5s, 6s, no 7s, no 8s, no 9s, etc. Okay? So they're not contiguous. They're not. They are in order, but you need to know which, for crop type 11, you need to know that you're looking at the 8th element. And then you go back to the list of names, and you look at the 8th element, and that's tobacco. Okay? So you can mix them up, you can match them up, you just need to convert to index. Let me show you how that works. We've got this frequency histogram that we're already printing, so let's try and print that same thing with names instead of numbers. And it'll all work out the same. So the names are called band class names. And the numbers, or the numbers are, or values I guess they're called, that one. And now, for our histogram, which we actually didn't stick in a variable, but we're gonna. We will get out the keys This is a dictionary, by the way, and we might need to tell it. How do we want to do this? Let me do it this way. I'll explain this in just a second. This is super fiddly, but it's a nice bit of fiddly to kind of show you more of the mechanics of how the system works. And there's a good chance I get it wrong the first time, so if you're typing it, careful. Fixed is what we'll call that. And something's going to fail. Numbers is a list. Sweet, I have no idea what happened. Yeah, I do. Fix.values.flatten. Key and value. One more try. There we go. I found my problem. My problem is that this is a histogram inside of a histogram inside of a dictionary. There we go. Woo! All right. So I'll explain everything that just happened, but it was a little fiddly. My reduce columns call way up there that produce the histogram returns an object with something in it called histogram. And that histogram is a dictionary. The keys happen to look like numbers, but they're actually strings, and the values are the number of pixels. So my names, my class names are a list. My values are a list. Get the histogram dictionary out of the result. Make sure it's a histogram. Make sure it's a dictionary. And then I'm going to map a function over each of the key value pairs. And for each key, right, that's the number 3, for instance, parse it into a number, get its index in the list of numbers. So it actually will be the third one. 4, 0, 1, 2, 3, 4, 5, and 6. 7 doesn't exist. 10 is number 8. Right? So if the key is number 10, the index will be number 8. Get the name number 8 and return the name along with the actual value, which we haven't done anything with, as a list. So what dictionary.map does is for every key, run the function on the key and the value and replace the value with whatever comes out. So my dictionary is now 10 is the key, and the value is the name and the amount. I'll print that and show it to you in a second. Actually, I can print it right there. Okay, so we turned 1 colon 1,000 into 1 colon corn 1,000. And then the dictionary constructor, the thing that makes dictionaries, knows what to do with key value pairs. Key value, key value, key value, key value. So we take all of these things that we just made, which are values, get all the values, flatten the list of lists into just one long list of key value pairs and turn that into a dictionary. Now, there's no reason you would have been able to intuit that from the 7 hours of training you've had so far. But that's why I want to show you. Those are some of the utility tools available to move lists around. If you're a Python programmer, you do stuff like this all the time. It's just not quite so fiddly. Yeah, so there you go. And the end result, dictionary with amounts. Okay? I think we got time for another question. Or we can be done. If there's really nothing else you want to see, your brains are full, aren't you? 3 hours is tough. These workshops are intentionally 3 hours plus a little more, just so you can kind of see what's happening. Uh-huh. Yep. The question is, what do you do about Landsat 7 gap filling? And the answer, our preferred answer, is to do a composite, a temporal composite. So you take a couple months and you composite them together. Or you take May from 3 years and you composite that together. But you overcome those holes with more data. Some people, the Colombians I was just talking to, they're filling in with Sentinel, which is an interesting choice. You can do it. Sentinel 2. They want to use Landsat, but where they don't have Landsat, they fill in with Sentinel 2. No. I didn't say it was a good choice. I just said it was a choice.
Yeah, the question about the cloud masking. Is there any way to do just the process rather than relying on the metadata of the areas of the study that were interested in?
No. I mean, you could. So the question is, can you do cloud masking from just the metadata for your region, right? And the answer is, sort of. You could just filter down to only 0 cloud images with metadata and then hope for the best. And generally, that metadata is pretty accurate. And you would have a whole bunch of images that have no clouds in them at all, but you're doing masking by avoidance. At the per pixel level, the metadata just doesn't have any information about the per pixel cloudiness. So you can't do anything there. You got to hunt it down. In the examples, we have a cloud score example, which actually works pretty good. It doesn't use any of the methods that the providers are using. We're about to publish a paper on it. It's actually simple cloud score, but it works really well. And you can use it temporally. The way that we use it is you compute a cloud score for every pixel, but that's a relative cloud score, and it doesn't really mean much. Lots of people just threshold that, but that's a bad idea. What you can actually do is stack up all the cloud scores for a particular region and see what's the bottom. The least cloudy pixel is likely to be some number, let's say 25. And then you can say, OK, anything from 25 to 35 is good, and anything above that might be bad. So you keep some percentage of the relative cloudy score based over time, and then throw away the ones that have a higher cloud score for that pixel. Simple cloud score in the example.
I applied the same approach for spectral unmixing, so I selected images with the low score of cloud.
Yep. Or the pixel with the low score. Yep. One second. Yep. So I didn't even mention fusion tables. So if you want to upload a shapefile into Earth Engine, you click the upload button, you upload your shapefile, you're done. In the next few days, we are announcing, I hope it's a few days, but it's Christmas, you don't know. In the next few days, we're announcing a CSV upload as well, so you can upload your CSVs directly into Earth Engine as well. If you have some other format, the answer to date about what you do with that other format is you put it into another product called Fusion Tables, and then we have an integration between Fusion Tables and Earth Engine to let you use that table data in Earth Engine. just like you would make, it's just a feature collection. It just happens to be a Fusion Tables feature collection. We announced Tuesday that Fusion Tables has kind of hit its end of life. You got one more year to use it, and then it's going to get shut down. And we're not unhappy about that. It's kind of an old product. It's a little crufty. There's not a big, robust team working on it anymore. We're happy to see something else come along. It's just, what is the something else? And so there's a lot of options, but none of them quite hit the needs that Fusion Table has been working well for. You can put your data into BigQuery, which is designed for really big tables, and we're working on that integration right now. You can put your data into Google Sheets, which doesn't have any real geospatial capabilities, but that's okay. If you stick GeoJSON in one of those columns, we can figure it out. And we're working on that integration right now. And the nice thing about Google Sheets versus Bigtable or Fusion Tables or Earth Engine tables is that they're writable. All those other ones are not writable. There's no way to update data in them. Whereas Google Sheets, with our interactor, our interface, you'll actually be able to update the sheet from your Earth Engine code. The downside of Sheets is that they have a limit of 10,000 rows or something like that. So they are good for fast, small interaction. They're not good for these really big tables. So if you have a ton of data and you want to update it interactively, there just aren't good options for that. And we're working on yet another feature, yet another product to try and make that work better. So the common joke in and around Google is that we deprecate the old thing before the new thing is ready. It's not a joke. We do that all the time. That's sort of what happened. But we've got a year to sort of untease this mess. And it affects me just as much as it affects you. Like everything we just did, that's stuff I do on a daily basis, right? I really need that to work. So we won't leave you hanging. If we get to the end and we're not quite ready, we'll just make the Fusion Table team not shut it down until we've got something better to replace it with.
The question about when we map add layer, and in that, can you show an example of how to get the min-max automatically chosen?
Sure. Sort of. If you're actually using this to do visualizations in map add layer, you've got a problem. Because this is a number that exists on the server in the future, and the min-max in your map add layer is a thing that happens right now. So you can visualize with it, but you have to do it another way. So you can manually call visualize, which is what map add layer does for you when you specify a min and a max in a palette. And then what's left should work. Okay. And because visualize happens on the server, you get the future values, and it will work out just fine. And one of these, I think that one, yeah, they're stretched. Okay. So you can stick the palette in there as well. So visualize is that function that's done for you automatically.
And this should work in Python, Jupyter.
Yeah. Everything you've seen will work exactly the same way in any of the languages we support.
Do you have any updates on the higher order classification techniques, machine learning, TensorFlow?
Hey Nick, what do we know about TensorFlow?
TensorFlow, the way it works right now, the way TensorFlow and Earth Engine work right now is that you can export training and testing data as TF record. You run your TensorFlow model outside of Earth Engine,
and an entire mailing list for Earth Engine TensorFlow stuff. So if you want to know about that as well, we can get you added to that.
Yes. So we're still working out the details of that, but what we hope to do is have some Holdout notebooks that demonstrate everything from just installing Earth Engine into a notebook to doing more complicated things to our teaching online training and so on and so forth.
There is a GitHub repo with several collab something's already in it that do some of those things already. Do you remember? Do you know? Nope. Nope. The community. I think it's the. I think so. GE community is a small group of users that have just decided we're too slow, and they're out doing their own thing. And they do some amazing stuff, and they sort of force us to do well. They shame us into doing some stuff that we should have done a long time ago. They, for instance, built the first code modules, and then we said, you know what, we really need to get our code modules out, and then we launched code modules. You guys have no idea what a code module is. You can take your script, break it into some functions, add a couple of lines, and then make it so that you can import that script into another script. And that's called require, and you require that script into your script, and then all those functions are available. So there is code reuse in JavaScript, so you don't have to paste everything into your big, into one giant script. Yeah, just the docs talk about that really well. It's just knowing it exists is the important part. Alrighty, if you're out of questions, we can be done.
One last question.
Yep.
Any developments happening in the code editor interface by itself, like making it just a little bit more user-friendly?
Yeah, user-friendly. It's super user-friendly. So be careful here. I love the code editor. I built the code editor. It's my baby.
In terms of the listing of the,
I'm aware. It's got problems. I know it has problems. We have a whole new front-end team now, 3 people, I believe, that is figuring out what's next. 4 people, and the thinking that they've gotten through so far is, we know that you need all the functionality in the code editor. You just may not need it that shape. And so their current thinking is, well, first of all, we're going to take everything in the code editor and break it into Angular components so that you can build your own code editor the way you want it. So if you want 2 windows for typing, great. We'll give you 2 editors or 3 maps or whatever it is. Put that together into the components that you want. And I'm cool with that. That's like, yeah, sure. This is a almost 10-year-old design. What is it? It's a 7-year-old design.
Getting the map component
into another window. You bet. Right. So components is the way they're going to do that. And then what happens after that is a little iffy. An interesting side effect of breaking that into Angular components is that those components are then usable in Python notebooks as well. And I was like, that's cool. I'm down with that. There have been a lot of crazy ideas about what to do with the code editor, and I just keep shooting those down. So I'm the reason it hasn't happened yet, but they're trying. They are trying to do, they're trying to meet your needs, and I am. They're trying to do a good thing, and I'm trying to make them do a good thing. And so we just meet in the middle, and I try to keep all your needs. I mean, I think I have a good idea what your needs are, because I use this thing every day, all day long. And I just advocate to make sure that it keeps doing what you need to do, so that you don't get, a text editor built into Google Earth with you got to make your own GitHub repo, and like I think I know what you guys are capable of, and that ain't it. So yeah, we're collaborating a lot on what that should look like, and they have some cool ideas. No timeline. I don't know what that. It could be a month. It could be a year. I don't know what that timeline looks like. How we doing on Earth Engine apps on a phone?
Works great.
Sweet. Done.
Yeah, so as part of that componentization
We're aware.
It's a little awkward. One workaround that I've seen be somewhat effective is instead of serving your app directly through the Earth Engine apps site, you can embed those apps in maybe another website that you have, a personal site, academic site, and there you can fiddle with the scaling of the component, the size of the expected. There's HTML details there.
More fiddling. All right. The only thing that I can think of to talk about what's left is what our plans for the year look like. I can tell you about that if you want, or we can be done. Any thoughts? Yeah, I don't think so. No? Yes? What do you want to do? Hear about? Okay. You want to be done? All right. Okay. So we pivoted a little bit this year in the way we are trying to get things done. If you were here yesterday and the beginning of my talk, I mentioned that a quarter of my team is oriented towards solving society's problems. And we decided we weren't doing enough of that. I love you guys. I love that you're doing science. I love that you produce papers. But a lot of cases, you're an academic, and the paper is the final result. And you don't really have the resources to make the app and keep it up and running. And you don't really have the resources to get the UN to use your app. And so of the 20,000 people that are trying to publish with Earth Engine, I wasn't happy that many of the cases we just ended with a paper and that was it. So we pivoted around this a little bit this year to have a lot more hands-on, in-depth, what we call impact, to try to force more impact with groups like the UN, with the Global Covenant of Mayors, with a few other of these large organizations that are in a pull mode. Like the UN has some problems and they really, really want a solution, and they're like, can you help us with a solution? And actually we can. So I think I showed this yesterday as an app, but one of those solutions is this web page we built for countries to be able to get statistics about the surface water in their country over time. It's a nice Earth Engine app. It gives you easy access to statistics, CSVs, downloads, all the things you need to report to the UN about your sustainable development goals, specifically around 661. So this is sort of a template for where we're headed. We're trying to find these large organizations that will pull, and then we find scientists that have solutions, and we connect them, and we're the glue often to help them do that. And so that was a very long way of saying one of our 3 big goals for the year is a set of code modules to make these kinds of analyses trivial. More and better compositing, more and better cloud masking, more and better gap filling. Like, I think I have a pretty good idea the 15 things you want to do to the point where you now run a classifier. And we can make that easy so that not everybody has to go through all those steps of cloud masking and gap filling. And even the cloud masking, even the Sentinel-2 and Landsat cloud masking isn't quite good enough. So new and better cloud masking techniques to just sort of remove all that grind out of the way so that you can get down to the new and better science. So a whole big pile of code modules for things that look like land cover classification. That was one. Number 2 is TensorFlow. We got a whole team banging out stuff to make TensorFlow work, and we're using some sample applications to make that work. We were just fighting on at dinner 2 nights ago about which of those applications we're actually going to drive forward. But the goal is to have some networks, some models that are useful to you, like maybe a cloud masking model or a land cover model or a land use model. That would be awesome, wouldn't it? Or a building detector, right? So we have this big long list of all the models we want, and we're just trying to figure out which one to do first. And then we're using that to drive our ability to produce new TensorFlow tools so that you don't have to do all the crazy cloud ML stuff necessary to build and operate a TensorFlow model right now. So to some extent, that also looks a little bit like land cover or land use classification. It's not quite sure what those models are, but if one of them is buildings, like a building detector, well, that technically falls into land use or land cover. So modules, TensorFlow, Oh yeah, okay. And then so there's a whole bunch of these data collection tools around in the world. There's Collect Earth, there's Open Data Kit, there's a bunch more. We like them, we support them, but they're difficult to just pick up and reuse. Like I can't go take Collect Earth and give it to you right now and say, okay, let's map palm oil. It just doesn't quite work that way. So we're trying to put in all of the tools necessary to build something like Collect Earth or one of these data collection tools right in Earth Engine. And we're just, right off the bat, writable tables is one of the problems. Like there's nowhere to put the data that you collect. So we're fixing that with writable tables. There's like 3 or 4 features that are necessary to make a new collection app in Earth Engine. And so that's sort of our third goal for the year, is to make it possible to make things like Collect Earth or TimeSync or one of those tools right in Earth Engine, and hopefully build the best in breed one of those while we do it. So land cover prep tools, new classifiers to do land cover land use, new tools to do validation collection. Hopefully, we think, as we're building that validation tool, we will be able to build an enormous repository of collected data. For the JRC surface water product, those guys made 280,000 expert-built points. I want that data. I want to be able to give you that data so that you've got 280,000 prime water training points. For the I'm doing this global urban project, urban mapping project. We had 1 million points collected. I want to have an urban, non-urban data set for people to download. And so I'm trying to collect all these really big data sets for validation purposes and put them into essentially a validation platform so that you can just show up and validate your data against someone else's data set that has hopefully been published and reviewed. And you can say, I have an 83% accuracy against the JRC water data set. And then in February, no, that's more or less our whole year for the whole team. We have more items on the list that if we get through with those, we will be adding, but that's our main goals for the year. Sometime around September or October, we haven't quite decided yet, we have a big user summit. The last one was in Dublin, the next one will be in California. It's 300 Earth Engine users doing crazy stuff for a week. It's one of our favorite conferences in the world. The nice thing about being at Google and running a conference is you get to do all the stuff you like and none of the stuff you don't like. So we just threw away the parts of the conferences that we don't like, and we do all the stuff that we find enjoyable. And most of the users that come say it's the best conference they go to all year. So I highly recommend it. It's a blast. It's way more information than you could possibly fit in your brain, but you will leave a much better Earth Engine user than when you showed up, I hope. I guess you could be worse. Do you think that happens? I don't know.
Probably not. It's probably in September.
Yeah, probably in September.
Any training coming up?
I am right this second trying to decide yes or no on a training in Buenos Aires in January. I'm going to be spending a lot of time in South America this spring for a whole bunch of deforestation stuff, kind of all over South America. And like the one in Buenos Aires, it's like as I go through a town, if it's convenient, I will try to have a workshop. Unfortunately, I announced this workshop, or I didn't even announce it. I asked people, so if I was going to have a workshop, would you want to come? And 150 people said yes. And I'm like, now what? I'm in Buenos Aires by myself trying to train 150 people. I've got a lot of staff here. I don't have that staff there. It's tough. So I will announce where those workshops happen at least a month in advance. I don't know where they're going to be yet. I don't know when timing works out for that to happen, but yes.
If you search for Earth Engine announcements, there's a mailing list where we send those announcements.
Right.
I don't know how you all found out about this. I heard some people just like, oh, my colleague mentioned that there's a training.
Right.
No, there's an email list. That
Definitely you want to be subscribed to the Earth Engine announcements list. It's super low traffic. It's like 2 emails a month, not like the users forum, which is like 2 emails a minute. We certainly announce our stuff in the users forum, but we also announce it on the announce list for the people that don't want to deal with the users list all the time.
So you said it's more of the floating fusion table capability.
Yep.
Apart from ingesting data with the table upload, is there any other way
Right this minute, no. Table upload's the only option. Yep. But we're adding a bunch.
Question. You spoke about taking this results that we find from a paper to people who actually need it. So is there that kind of a platform that you might provide? If I have some result and I ask you or some platform that can scale it up, take it to UN, is that an option?
The connecting is a little tricky because we don't really have any infrastructure in place to do that. It's all one-offs right now. But step one is get an app built that does what you want to do, and then we see what we can do with it. So
you published a paper with the global forest cover change.
Hmm?
So some collaborators were from Google, some were scientists. So if we are interested in something of that sort, who should we talk to?
You should send an email to earthengine@google.com with what you have in mind. Just be aware we're super picky about how we pick those strategic partnerships on axes that you totally don't care about. Like how likely is it we'll be able to reuse this for another project later, things like that. So certainly you can ask, and that's how we learn about lots of these things. But don't be disappointed when we say we don't really have the resources to do that right now. All right. Well, thank you very much for coming. When you do good stuff with Earth Engine, we definitely want to hear about it. So send us an email or say something to the users forum. And now go do good stuff. Thanks.